Students, we will continue with the rotational motion chapter, and this is the third in the series, third class in the series and the last one. We will talk today about moment of momentum, which is also called the angular momentum, moment of force called torque, then conservation of angular momentum, which is very interesting part, and there are some examples we may consider, then comparison of linear and rotational motion. So, what do I mean by moment of momentum? What is momentum? In linear motion you have studied, if a body of mass m moving with a velocity v, then it has a momentum p equals to mass into velocity. So, it is a vector quantity in the direction of the velocity and its magnitude is m into v. Moment of momentum is the corresponding quantity in rotational motion. In rotational motion, when a body of mass m having a momentum p is rotating, its position vector is r. If the particle has the position vector r having a momentum p, then the moment of momentum, whenever you come across the word moment, means there must be, it is that quantity is multiplied with the perpendicular distance from a certain point. So, in this case the moment of momentum is vector, it is a vector quantity which is the cross product of position vector and momentum of the body. So, in this case, if the body is placed at this point, at the point A, let us say, having a momentum p as shown, and it has a position vector, that means this is my origin. From the origin, the particle A is placed at the position vector point is r, then r cross p. So, it is a cross product. So, you have to apply the cross product rule. If I go into the magnitude of that thing, L is the angular momentum here, the magnitude of L will be, if you take a cross product A cross B, magnitude is A B sin theta, where theta is the angle between the two vectors. So, here r cross p is r magnitude plus into p magnitude into sin theta, where theta is this angle, theta is the angle between r vector. If I draw the r vector here, I can always take this vector to this point. So, I can, this angle will be theta, then the magnitude is r p sin theta. Or if you take mass, if m is the mass of the body and having a velocity, so p is m into v. So, I can write this as r, let me this is the magnitude of that thing, into m v into sin theta. Now, in the case, special case where r is perpendicular to p, this angle is 90 degree, then this becomes equal to m v r when theta is 90 degree, when r vector is perpendicular to p vector. So, this is the maximum value, m v r will be the maximum value. Now, if it is rotating, suppose this body is rotating in a circle with an angular velocity, if the angular speed is omega and it has a direction, I will tell you. If the angular velocity is omega, then you know that linear speed is equal to omega times r. I am taking only the scalar quantities. So, in that case, I can write L, in that case L magnitude, or this value is m v jagare mu r omega lekhibi jodi, r omega a gote r, tenu m r square omega, r omega into r. So, this comes out to be m r square omega. So, for a single particle which has a mass m moving with a velocity v and its m has a position vector r, and if it is rotating with an angular speed omega, that means the angular speed of this is omega, then we can say the angular momentum of that particle will be m r square omega. Now, m r square, you know already that this is moment of inertia of the particle. So, for a single particle also I can write the angular momentum can be written as I omega. This is all about the magnitude part. So, I have talked about the magnitude. What about the direction? L is a vector. So, the direction L has a direction R cross P. So, you have to find out the direction of the cross product. So, in that case, suppose R is along this direction and P is along this direction. Let us say first of all L is perpendicular to plane containing R and P, R vector and P vector. Let us say R vector and P vector are lying on this plane of this board. Then your L is perpendicular to this board. Now, perpendicular directions, there may be two directions, either towards you or away from you. How do I know that? So, keep your right hand with all these 4 fingers together and keep it on R, turn it towards P and close your palm. So, in that case, this is the direction of thumb gives you the direction of A cross B or R cross P. So, keep on the first vector R cross P, R is my first vector, P is the second vector. So, take your right hand with all your fingers like this, such that your this will face towards the second vector. So, P is on this side. So, I have shown it towards that side. So, I keep it on R, that means this line is on R, then I am turning it towards P, the direction of thumb gives you the direction of L. So, this is in this case it is towards you, towards the reader. So, this is perpendicular to the plane containing R and P, and either it can be towards you or away from the reader. So, depending upon whether it is R cross P is towards you or away, it will have a direction. So, L is always perpendicular. Similarly, you can see that here omega is also a vector, and omega is always, if a body is moving with an angular velocity omega, omega is along the axis of rotation. If it is anti-clockwise, if the motion is anti-clockwise, then omega, the direction of omega is along axis, along this axis. So, angular momentum can be found out this. Let us take the case of angular momentum of a rigid body. Suppose this is a rigid body and it is the axis of rotation. Now, when a rigid body rotates with a certain angular speed or angular velocity omega, then each particle of this body will move in a circular motion around the axis of rotation, around their centers of rotations will lie on this axis of rotation. Let me take this rigid body as the congregation of or sum of, or let me divide this whole thing. I consider that the rigid body consists of many particles, n particles, each of M1, M2, M3, Mn mass. So, M1 mass is at a distance of r1 from the axis of rotation, from its center of rotation. Similarly, M2 is at a distance, perpendicular distance r2 from the axis of rotation, and similarly for Mn. So, all there are n number of particles. I am not drawing all of them, it becomes clumsy. So, if it is so, then what is the angular momentum? The angular, I am taking here that the omega is constant and it is along the axis of rotation, L will be along the axis of rotation, L will be along the axis of rotation. So, I am taking all the magnitude part, because R and the momentums. Now, all these particles M1 will move in a circular motion around this axis of rotation, and at every point of their rotation the velocity, linear velocity is along the tangent. So, tangent and R. So, if V is along the tangent means momentum is along the tangent, m into V. So, m into V, M1 V1, let us say it has a velocity V1, because that depends on the distance from which it is at which it is placed. So, V1 is along this direction, R1 is along this direction. This is the axis of rotation. Let us imagine that this is the axis of rotation, this is your R1 and this particle has a velocity V1 away from you in this manner. So, it is perpendicular. So, if it is perpendicular, then theta is 90 degrees sin 91. So, mVr will be your angular momentum. So, the first particle will have the angular momentum. I will write for the first particle m1, it is at a distance of r1 and it has a velocity v1. Similarly, for the second one, it will be m2, r2, v2. So, I take v all these v's, v are the velocities of the corresponding particle of particles. If it is v1, it is means it is for m1, v2 is the velocity of m2 and so on. So, I can add up till the n number of particles. So, mn, rn, vn. Now, this is equal to, if I put the value of v is equal to r omega, then v1 will be equal to, so v1 will be equal to r1 omega, v2 will be equal to r2 omega. Distance into angular speed, all of them are moving with same angular speed. Remember that when a body is rotating, all the particles have the same omega, same angular speed, but their linear speeds are different. V is equal to r omega. So, if r is different, then v is different, omega is same. कहीं ना गोटे पार्टिकल एठी अछि सीए गोटे थर बुली आसिया को जतिकी टाइम नब आर पार्टिकलटा भी सेतिकी थर नब नहले जदि अलगा टाइम नब ता माने सी ये पूरा 360 डिग्री पहुंची बुली गला बेलको आरटा जदि 360 डिग्री पहुंचन तो ता माने बॉडीटा भांगी गला व्हिच इज नॉट द केस हियर आमर रिजिड बॉडी से जे जोडी थिले सेट रहबे तांका तांका भीतर डिस्टेंसटा चेंज होबनी सो दैट इज व्हाई द जड़े जदि 360 डिग्री बुली बुलिकी आसला आर जनक मध्य 360 डिग्री बुलिला ताने एका टाइम रे से बुलिले सेतिकी सो 360 डिग्री इज 2 पाई सो द ओमेगा विल बी इक्वल टू 2 पाई डिवाइडेड बाय द टाइम दि समस्तंकर टाइम समान तेणु 2 पाई बाय टी समस्तंकर समान सो दैट इज व्हाई एंगुलर स्पीड ऑफ ऑल पार्टिकल्स आर सेम सो v1 will be equal to r1 omega, v2 is equal to r2 omega. You can write till vn. So, if I put this will be m1 r1 square omega plus m2 r2 square omega plus and so on mn rn square omega. Put the values of v here and you will get this. So, this is equal to omega times m1 r1 square plus m2 r2 square and so on mn rn square, and this is nothing but the moment of inertia I. So, this is moment of inertia of the body about the axis of rotation from which we have measured these distances r1 r2 etc. body about the axis of rotation. So, for a rigid body also, for a single particle it is also I omega, and for a rigid body also the angular momentum L is equal to I omega. I am taking the scalar part, I am taking the magnitudes only, and L is along the axis of rotation in all these cases. So, L is equal to I omega. So, angular momentum actually is something like momentum. Momentum contains the quantity of motion in a body. Similarly, your L or angular momentum will tell you the quantity of rotational motion in a body. How much is the quantity of rotational motion? So, let us move over to the next part, the moment of force. Very similar to moment of momentum. Be careful, it is moment of momentum. Momentum is P. Linear momentum रा moment. So, now in this case if you look at the diagram, r sin theta can be said as the perpendicular distance from the axis of rotation. So, this will be equal to mass into velocity into the perpendicular distance, because if you draw the diagram, the perpendicular distance एठु जदि एमती पकेइबा आमे गोटे perpendicular draw करिबा, this is r sin theta. that you can also write it that way, which is r perpendicular mu lekhi deli seti r sin theta jaga re r perpendicular lekhi deli. So let us go to moment of force. Moment of force, which is also called torque. As I have already told you, moment means some perpendicular distance is to be multiplied with the quantity whose moment you are finding out. Moment of force will be the perpendicular distance from the axis of rotation into the force, and the vector relation, vector definition is tau equals to tau, this is pronounced tau, is equal to r cross f. So instead of p, if a body has a position vector r and it is acted upon by a force is acting on it, this is the center of rotation, about this the body is rotating, and the line of action of this force is not passing through O, then there will be a torque. This torque tau is the moment of force r cross f. So torque is r cross f. R is the position of the particle which is experiencing a force F. As before, I can produce this OA and this angle is theta. So this angle is also theta. I drop a perpendicular from the center of rotation. This is my center of rotation, about the center about which the body is rotating. So from the center of rotation, I have dropped a perpendicular on the, this is the line of action of force. So if I drop a perpendicular, sin theta is perpendicular over hypotenuse, from here to here the magnitude is r. So sin theta is perpendicular by r. So r sin theta is this perpendicular. So this is your r, this is r sin theta. So tau magnitude is equal to r cross f. A cross b ro magnitude hochi a b sin theta. So r cross f ro magnitude haba r ro magnitude f ro magnitude into sin of the angle between them. एठी मु देखैछि r आउ f मध्यरे कोण होछि थीटा. So r f sin theta, I can write r sin theta as this perpendicular distance. So f magnitude को मु आउ गार दउनी, understood that it is the magnitude only. F into perpendicular distance between or between from the center of rotation, from center of rotation perpendicular distance from center of rotation of line of action of force. See, when you are rotating, or you suppose for example you are opening a door. When you are opening a door is hinged at some point and you want to open it. So when you want to open it, you are applying a force. If you apply the force near the hinge, जो hinge लागिची, डोर टा एमती लागिची हिंज जो सेठी जदी हिंज दबो, हिंज पाखरे फोर्स अप्लाई करिवो, किछि एटा रोटेट करिवो जीवनी, किंतु जदी तमे दूर रे अप्लाई करिवो सेति पय हैंडल टा सब बेले डोर रो हैंडल सब बेले लास्ट एंड रे थाए, सेठी धरि कि तमे ओपन करिवो. सो व्हेन यू आर अप्लाइंग ए फोर्स एट ए लॉन्गर डिस्टेंस, ता माने आर टा बेसी अछि, तेनु टॉर्क सेठी बेसी हबो एंड यू कैन रोटेट इट इजीली. किंतु तमे जदी धरिकी कबाट बंद थी तमे एठू तार जोठी जस्ट हिंज पाखरे जेते फोर्स देले भी से रोटेट हेकरी खोलिबनी, रोटेशन कैन नॉट बी मेड. सो टॉर्क इज द वन व्हिच कॉजेस रोटेशन, just as force in linear motion causes the linear acceleration or it changes the state of rest or state of uniform motion of a body in linear motion. Force jaha kama kare in linear motion, torque the same work kare in rotational motion. Force changes the state of rest or state of uniform motion in linear motion of a body, whereas torque produces rotation or it changes the state of rotation of a body. So, for rotating body, what we require is a torque. That means, force should be applied and it should be applied away from the axis of rotation or the center of rotation. That means, r should not be 0. You have to apply F, and you can the angle theta, if the angle theta is 90 degree, then the torque applied is maximum. So, this is the work of torque. So, torque produces rotation, force produces linear acceleration or changes the linear motion of a body. So, if you want to start motion, then you start linear motion, you must apply a force. If you want to start or change the rotation of a body, then you have to apply a torque. So, whenever there is a force not acting not in the through the center of rotation, there the perpendicular distance, there must be some perpendicular distance or the axis line of action should not pass through your the center of rotation, then there is a torque on the body. Now, torque can be, so if it is r cross f, let me take that for simplicity, we take r and f perpendicular, so that the magnitude will be maximum of torque. So, torque if theta is 90 degree, when theta is 90 degree, theta 90 degree mane r au f bhitere konota 90 degree, ta mane r au f perpendicular, r is like this, f is like this. So, r and f are perpendicular. In that case, tau magnitude, tau is equal to r in simply r into f. When r perpendicular to f, or in other words, you can say the perpendicular distance into the force, magnitude of the force. This is the magnitude of the force. Now, as before, if we calculate the for a rotating body, suppose a body is rotating, it is at r and the force is along this direction, and body is rotating in a circle of radius r. What is the relation between our torque and angular acceleration? If you remember, in linear motion, we express the Newton's second law, force is equal to mass into acceleration. Linear acceleration, A is linear acceleration. I have already told you that the corresponding quantity of force in rotational motion is tau or torque. So, torque will be equal to, now mass in rotational motion is moment of inertia. Then what we expect is A, linear acceleration should be replaced by rotational acceleration. Rotational acceleration, angular acceleration is written as alpha, where alpha is angular acceleration. So, this in rotational motion, this is the corresponding equation. Again, tau r into f. So, if I take this, relation with angular momentum. We have L is defined as r cross p, your tau is r cross f. These are the defining equations. Now, let us take dl, let us time derivate. Take the derivative of L with respect to time. This will be equal to, now there are two vectors. So, first function derivative of second plus derivative of first into the second. Now, this is equal to r cross dp by dt, rate of change of linear momentum, that is force. So, this is r cross f from Newton's second law. Force is rate of change of linear momentum, p is momentum. So, dp by dt is change of momentum per unit time. So, r cross f plus this is dr by dt, rate of change of displacement, that means this is rate of change of position, means this is velocity. So, this is velocity into, now momentum is mass into velocity. Now, velocity cross m is a scalar, सेटा एठी लेखिले जहा एठी एपटे लेखिले सेया, तेणु v cross v. Now, a cross a, any quantity a cross a, तार magnitude जदि बाहर करिबा, a रो magnitude आउ sin of the angle between them, a vector आउ a vector दीटा को तो एका ता उपरे ता माने angle हला 0 degree. So, this will be 0. So, cross product of a single vector a cross a is 0, तेणु v cross v will be 0. So, this part will be 0. So, I am left with r cross f, and this is nothing but tau. So, this gives me the relation between tau and dl by dt. Tau is equal to dl time derivative of angular momentum. See, if you go to this, f is equal to, f is defined as rate of change of linear momentum. So, the corresponding equation will be f jagare mu lekhibi tau will be equal to rate of change of linear momentum jagare angular momentum. So, the corresponding equation of that f is equal to rate of change of linear momentum becomes tau is equal to rate of change of angular momentum. And similarly, your tau can be written as I into alpha, where alpha is angular acceleration, where omega changes, omega is not constant. If omega is changing, in that case you can write this as tau is equal to I moment of inertia into alpha. Then conservation of angular momentum. So, in which case angular momentum will be conserved. You have read in linear motion that the conservation of linear momentum, that when external force is 0, because your f equals to, so this is the conservation of angular momentum. So, let us discuss conservation of angular momentum. In linear motion, always compare with the linear motion, because that is much easier. Linear motion, you say that when f, because f is equal to dp by dt, when f is 0, your dp by dt will be 0, ta mane p is constant, linear momentum is constant. This is how you take the conservation of linear momentum in linear motion. In rotational motion, very similar, tau is equal to r rate of change of angular momentum. When the system is isolated, or you say that the external torque on the body is 0, when external torque on the system is 0, then total angular momentum is conserved or constant. Remains constant with time. Because see, when tau equals to 0, means dl by dt is 0, गोटे जिनसर जदि टाइम डेरिवेटिव टा 0 तामाने से l टा constant, से quantity टा constant of time. So, that gives us L is equal to constant of time. गोटे कांस्टेंट डेरिवेटिव होची 0 कांस्टेंट ऑफ टाइम सो एंगुलर मोमेंटम इज कंजर्व्ड. Then there are various examples of rotation in which case the torque applied on the body is 0 due to which the angular momentum remains the same. Best examples are all the you take a somersault or somebody who is diving, a swimmer who is diving from a diving board, or a skater who is skating. Suppose a skater is skating, let us say a skater is skating with arms outstretched like this, and she is rotating. Suppose this body is rotating, this one is rotating with some omega. Now our L, you remember, is equal to I into omega, moment of inertia into omega, keep that in mind. Now in this case this person was rotating with arms outstretched out दूर को अच्छी तामाने यही पार्ट ऑफ द बॉडी इज एट ए लार्जर डिस्टेंस फ्रॉम द एक्सिस ऑफ रोटेशन. दिस इज माय एक्सिस ऑफ रोटेशन जहाँ चारिपटे मु एमती बुलुची. सो यही डिस्टेंसटा दूर रे अच्छी ना मोमेंट ऑफ इनर्शिया हैला एम आर स्क्वायर. जदि आर डिस्टेंसटा बेसी अच्छी यही एम मास रो धर यही हाथर यही मासटार यही मास रो आरटा बेसी दूर रे अच्छी तामाने तार एम आर स्क्वायरटा बेसी. तेणु मुझे हाथ स्ट्रेच करके रखी माई मोमेंट ऑफ इनर्शिया अबाउट दिस एक्सिस ऑफ रोटेशन इज लार्ज देन व्हेन आई कीप माई हैंड्स क्लोज बाय कहीं मो पाखक जो आनिली बर्तमान मोर यही मास गुड़ाक मोमेंट ऑफ इनर्शिया जो एक्सिस अच्छी एक्सिस टू पाखक पड़े आसला. सो नाउ द डिस्टेंस आर इज लेस सेही मास अच्छी मास इज नॉट चेंजिंग बट द मास इज नाउ एट ए लेसर डिस्टेंस फ्रॉम द एक्सिस ऑफ रोटेशन सो द मोमेंट ऑफ इनर्शिया डिक्रीजेस. So in this case what will happen that suppose this person हाथटा एमती दूर को होगी थिला now I am not a very good you let us say that it brings the hands close by. So in this case when the arms are close by the rotation suppose गोटे आइस स्केटिंग करुँच जो मैंने से स्केटिंग स्केट्स गुड़ाक पिंधि आउ रोटेट करुँच हाथ को दूर को रखिकी सीधा आसिले एमती हाथ को दूर रखिकी बुलवार अच्छी जिते हाथ को पाख को नहीं आसवे. सो व्हेन यू ब्रिंग योर आर्म्स क्लोज बाय योर मोमेंट ऑफ इनर्शिया डिक्रीजेस. व्हेन मोमेंट ऑफ इनर्शिया विल डिक्रीज आई डिक्रीज कले ओमेगाटा बढ़ी जीवो एल तो कांस्टेंट रहिबो. सो एल जदि कांस्टेंट रहिबो आई डिक्रीज करिगला तामाने ओमेगा बढ़िबो. ओमेगा कोन एंगुलर स्पीड तामाने जोर रे बुलिबो आ कोन. सो दैट मीन्स व्हेन इट रोटेट्स now in this case I is less and omega is large. So for all rotations all these the skaters ice skating जो मान करचंती suppose you are diving करचंती swimming pool रे diving करचंती हाथ outstretch करिक आरंभ करिवे diving कला बेले जते बेले in the air if you want to make a somersault what you bring your देखि जदि टीवी रे देखि स्विमिंग करला बेले बा निजे भी करि हाथ गोड़ को पाख को नहीं आसवे. सो व्हेन यू ब्रिंग योर आर्म्स क्लोज बाय एक्सिस ऑफ रोटेशन रु डिस्टेंस तुम हाथ गोड़र कमी गला. सो हाथ गोड़ जो जाकी दब तामाने तुम यू आर नाउ यू कैन रोटेट विथ मोर स्पीड. सो एंगुलर स्पीड इंक्रीजेस. सो दिस इज द केस व्हेन एल तामाने प्रथमे I1 ओमेगा 1 विल बी इक्वल टू I2 ओमेगा 2. इन दिस केस I1 and speed was omega 1. A case रे I2 is less omega 2 is large. I1 omega 1 I1 टा बड़ थिला बेसी थिला omega 1 जहाँ थिबो I2 is now less so omega 2 is large such that the product remains the same. There are several examples of this kind in rotation. I omega remains constant, so this will be remaining constant in this case when there is no torque is 0. So here no one else is applying a force on it, so the rotation thare arambh chaluchi mane se chalichi because we say that it is skating on a ice, so no friction, so external force 0 tenu torque is 0 tenu se I omega will remain constant. In the first case I is large because arms were outstretched. this part of the body was at a larger distance from the axis of rotation. So, you can apply, and many other cases you can apply the conservation of angular momentum. Similarly, suppose your earth is spinning with some angular speed omega. Now, if the moment of inertia, suppose mass remaining same, mu कहबी जे धर अर्थ टा हमर छोट होई गला, contract करी गला, mass remaining same contract होई गला. You know that the sphere is moment of inertia sphere is 2/5 mr square. ता माने r टा बर्तन कमी गला, ता माने moment of inertia less होई गला. Moment of inertia जदि less होई गला, ता माने omega will be large. What is omega? Omega is 2 pi by t. T केते ना गोटे थर पूरा बुलिबा पई 24 घंटा लागुची. 24 घंटा अच्छी वर्तमान, किंतु वर्तमान कौन हम ना से 24 घंटा ता माने ओमेगा लार्ज हम माने टी टा स्मॉल हम, ता माने टी टा तले अच्छी ना, टी इज स्मॉलर नाउ. एटी 24 घंटा थिला टी टाइम पीरियड गोटे थर पूरा बुलिबा पई ताकू 24 घंटा लागुथला, वर्तमान 24 घंटा जगह रे कम समय लागियो, ता माने ओमेगा स्पीड रे जल्दी स्पीड रे बुलिबो, ता माने कम समय रे बुली जिवो, ता माने आ दिनटा 24 घंटा हबनी कम हबो. सो डिपेंडिंग अपॉन हाउ व्हाट इज योर फॉर्मूला एंड यू पुट दिस r square times स्मॉलर हबो, ता माने स्क्वायर टाइम्स जदी हाफ हे जिवो एटा तबे स्क्वायर टाइम्स से हिसाब रे 1/4 हे जिवो. So, this is about conservation of angular momentum. Now, we will compare the two types of motion, the linear motion and rotational motion. We have completed all of the defining quantities of rotational motion, starting with angular speed. Angular speed is the angle covered per unit time, and all these cases we have assumed that our omega is along the axis and the axis is a fixed axis. All these examples. Conservation of angular momentum, similarly if you have not to केवे खेली not to खेलिले not to रे सेया not to रे सेमती not to टाको जदी खाली रखिबो that means top सुता एमती थाए एठी करिके ताको बुला जाए. If you put it on the surface से गड़ी पड़िबो एमती गड़ी पड़िबो एमती रही जीव. It is not तार सीधा ही रखी परिबनी, but when it rotates तमे ताको बुलाई के छाड़ी दबो से it remains, it doesn't topple down. धीरे धीरे अवश्य तार एनर्जी कमी गले से धीरे धीरे एमती बुली बुली के प्रथम पुणी एमिति एमिति हेकि बुलिबो प्रिसेस करिवो and then it will fall down. Its energy decreases because of the air resistance, but it continues to move because of the conservation of angular momentum. So, comparison करिवा. Linear motion and rotational motion. We will start with distance or the position. In this case, position is your distance s or r, whatever you say. This position is denoted by s, or any body is present here, you say that its position vector is s or r, jaha koi paro s or r. Rotational motion, here the displacement or the position is determined by theta. Position here is determined by the angle it has. Suppose this is the reference line, where is the body during rotational motion, where is the body or what is the angle it has made. So, position is determined as theta. Then the speed or velocity, linear, here we will say it is linear velocity. Linear velocity is dr by dt or ds by dt, or let me take it as r. And here the angular velocity is omega, which is d theta by dt. The instantaneous angular velocity can be defined as the rate of change of angle covered. So, d theta by dt. Then comes acceleration. Here acceleration is linear acceleration is A, which is dV by dt. The corresponding equation here is angular acceleration is alpha, which is d omega by dt. Then comes mass. The measurement of inertia is measured by mass. Here this is called the moment of inertia, mass m. The corresponding measure of inertia, moment of inertia, which is denoted by I. Inertia is the property by virtue of which a body opposes any change in its change of state or motion, linear motion or uniform motion, whereas moment of inertia is the property by virtue of which the body opposes any change in its rotational motion. So, corresponding thing is moment of inertia. Then the equation that you have is force is equal to all the equations that we derived. If you remember, V equals to U plus AT, S equals to UT plus half AT square, then V square is equal to U square plus 2AS, and we have the corresponding equation V is the final velocity or omega is equal to omega 0 plus alpha t, then S jagare distance theta is equal to omega 0 t plus half alpha t square, and V square is omega square is equal to omega 0 square plus 2 acceleration jagare alpha, S distance jagare theta. Then now we have the Newton's laws, force is equal to mass into acceleration. Now force aga kon eti force is the agency which produces linear motion, which changes the state of linear state of a body. So, it is the torque, the corresponding quantity is torque. Then force is equal to, it is related to mass into acceleration. It is also defined as rate of change of linear momentum ro chhad deli. Momentum, the linear momentum is P, is mass into velocity. Here angular momentum will be similarly angular momentum L will be equal to mass jagare amar achi inertia mass jagare inertia I, moment of inertia, tenu mass into velocity m jagare lekhibi I, velocity hala linear velocity, ta jagare lekhibi angular velocity. So, you can get, if you remember these relations, you can write the corresponding relation in rotational motion. So, L is equal to I omega. Then comes force is equal to mass into acceleration. Similarly, force jagare kon lekhibi na torque, mass jagare lekhibi moment of inertia, linear acceleration jagare mu eti acceleration, linear acceleration A, taro corresponding angular hela angular acceleration alpha. So, tau is equal to I alpha. So, force is equal to mass into acceleration jaha in linear motion, the corresponding equation in rotational motion is tau is equal to I alpha. Then conservation, if force is equal to 0, external force is 0, then P is conserved. Ethi amara if tau is equal to 0, external torque is 0, then L is conserved. Force, linear momentum, angular momentum, force, torque, dl by dt. Force is equal to, force is also, force can be written as, here I left one thing, F can also be written as rate of change of linear momentum. and here I can write force jagare torque. Torque can be written as rate of change of angular momentum. So, if you compare these things, you find that if you remember the linear motion equations, you can write the corresponding equations in rotational motion, provided you know what stands for what should be replaced by what. In case of linear motion, the distance is replaced by angle theta, velocity linear velocity v jagare ame ethi lekhiba angular velocity omega, linear acceleration a jagare lekhiba angular acceleration alpha, then inertia pai ame mass lekhuchu mass m, mass jagare lekhiba ethi moment of inertia I, capital I. Then these are the relations v is equal to u plus at एगुड़ा को तमर मुखस्थ होइकि थिबो सेई ता जगारे corresponding omega 0 is initial angular speed, omega is angular speed at time t, alpha is angular acceleration. So you can replace जहार जहा corresponding एटा भी initial speed, final speed को तुमे बा speed at time t. So force जगारे torque, linear momentum जगारे angular momentum, linear momentum जदि हला mass into velocity, angular momentum of mass जगारे I, velocity जगारे omega. So L is equal to I omega. Then comes your force रा दीटा definition कहउछ dp by dt नहले ma सेही थ्रू एटा बाहरिबो. So rate of change of linear momentum is mass into acceleration. एठी लेखिबो tau यार corresponding f जगारे tau, p जगारे L. So tau is equal to dl by dt. F is equal to mass into acceleration, f जगारे tau, m jagare I, moment of inertia, acceleration jagare alpha. So tau is equal to I alpha. And the conservation law, if external force is 0, then the total linear momentum is conserved. बहुत केस रे तुम देखिछ जो shooting a rifle, recoil of a gun, these are examples, or collision of two particles. These are in linear motion. We have studied these things in the conservation of linear momentum. I have given you some example of conservation of angular momentum, where we have to rotate. If I is changed, then omega will change accordingly, such that I omega remains constant. So if external torque on a system is 0, then the angular momentum will be conserved. So these are the comparison of linear and rotational motion, conservation of angular momentum, and moment of force, torque, and moment of momentum, angular momentum. So with this we come to the end of this unit of rotational motion, system of particles, where we started with the system of particles. There we defined the center of mass, how the center of mass, if external force F acts on a body, then the acceleration, there will be acceleration of the center of mass. It may so happen that the bodies are different parts of the bodies are moving with different velocities, but the center of mass moves such that external force divided by the mass will be the acceleration of the center of mass. So we started with the center of mass, then we found out moment of inertia, the parallel axis theorem, perpendicular axis theorem, and we found out the moment of inertia in different cases like ring, disc, etc. I gave you the formulas also. Then we came to the dynamics part, the momentum, what is angular momentum, then what is torque. Torque produces rotational motion. Anywhere you want to rotate somebody, you have to apply a force such that the force is not passing through the axis of rotation. तामाने कबाटा खोलला बेले आ पूरा हिंज जोठी अछि सेठी फोर्स देले लाभ नाही किछि, दूर रे देले it has a distance, तेनु distance बेसी अछि तेनु से बढ़िबो. जत्ते कि दूर रे तमे अप्लाई करिवो फोर्स, कम फोर्स रे भी खोला जाई परिबो, बट पाखरे दबदबी you require a larger force. If R is 0, then the torque will be 0. So torque should be, for maximum torque, R should be perpendicular to force, application of force. Then we have compared, we also found out the equations. These equations also we derived in the first class itself. I conclude this chapter with the comparison of linear and rotational motion with this table. So you can remember these equations, you remember what is should be replaced by what, then you can write all these equations. Thank you. बंद करो.